I wanted to put together a short video to summarize the major ideas of section 3.9 on antiderivatives. What we're trying to do here is answer a question like this. The derivative of what equals f of x? This is in some sense the inverse of what we had been doing before. We had been doing the derivative of f of x yields what, and now we're sort of going backwards from that. And this will kick off ideas that will run through chapter 4, chapter 5, and beyond. And so let's take a look at these definitions and all of that. Reasons you might want to know about this question, for example, if we had been given the velocity of a particle at time t, the answer to this question would be the position at time t. At time t. And so you can reconstruct a flight path based purely on velocity information up to a point, which we'll talk about. But this is one way of going from velocity back to position. So an antiderivative is a function is an antiderivative of f of x if g prime of x is f of x. So if you take the derivative of this and you get this function out of it, then it is an antiderivative. So for example, if our f of x were 2x, then one possible g of x would be x squared because the derivative of that is 2x. And so g of x equals x squared is an antiderivative of 2x. But that's not the only one. There's also g of x equals x squared plus 1. You take the derivative of that, and you also get 2x. You could have x squared minus 54, and you still get g prime of x equals 2x. In fact, you could take any function, any g of x, being x squared plus a number, or a constant. A number is an antiderivative of this x squared, of 2x. And so this prompts the idea, before we had one derivative, now there are multiple antiderivatives. This prompts the idea of the general antiderivative, where to counteract this, you could call each of these specific antiderivatives. But the general antiderivative of f of x is a family or a set of functions, functions g of x, so that g prime of x equals f of x. Now, the good news is that all the members of this family all pretty much look the same. They all pretty much have this structure of x squared plus a number for this f of x being 2x. This is a consequence of the mean value theorem back in 3.2. It's tucked in the very end of section 3.2. So by 3.2, any antiderivative, if it's on a continuous chunk of that function, they all look like the others. You just take the g of x plus, you take the original antiderivative you're interested in, and the other one's going to look like g of x plus c. And so in the end, the challenge is going to be going from something like 2x and coming up with whose derivative that is. I will also mention, while we're talking about it graphically, what's going on. Say I drew that 2x curve. It looks roughly like this. Y equals 2x. What functions have that as the derivative? Well, that y equals x squared does. But we also talked about how y equals x squared plus 1 is also an antiderivative. X squared minus 54, not to scale. And notice all of these are just, in some sense, parallel versions of each other. They're not going to intersect. not quite parallel because that word only applies to lines, but the distances between them. And the distance between them there and there is the same as the distance there and there, and that would be the difference between the constants that go with this. And so you take that x squared and you can shift it up by a certain amount or shift it down by a certain amount by adding a negative number to it, and you get all of the different antiderivatives. And we've noticed by now that shifting up the vertical position of a curve does not affect its derivative, because the derivative is just all about tangent lines. It doesn't matter how high that tangent line really is. So there's one last flip to this, and that is what is sometimes called an initial value problem. Initial value problem. Well, even though there are infinitely many antiderivatives, sometimes you want a particular one because you know, for example, the starting point of the plane whose velocity information you have. You know the starting point. It doesn't have to be the time at 0. So, for example, find a function f of x so that f prime of x is 2x and f of 3 is negative 2. What that's really doing is, all right, I want the curve among these. I want the family that goes through the point 3, negative 2. So I don't know where that is. Let's say it's around there. And so what we're trying to find is, in particular, the y equals x squared plus something that will run us through that curve. And so it's a fairly straightforward process in solving one of these. You want to take a look at, first find a general antiderivative, which in this case is fairly easy to spot. It's going to be x squared plus c. And then we've got to find the specific c. We've got to find the right c. And so the way we do that is, well, f of 3 is going to be negative 2, but f of 3 is 3 squared plus c equals negative 2. All right, well, that's 9 plus c. So that means c had to have been negative 11. And so the function that they're actually interested in, that has the right derivative and the right value at a certain spot, is x squared minus 11 plus negative 11. And so you can see that this one that would be running to that point would be also running through negative 11 down there. There's all sorts of other information then you can extract from that. But that's the baseline of it. The challenge a lot of times is going to happen going from the 2x to that x squared. I chose an easy example, but it does get harder. Sometimes for initial value problems, you get different information. Maybe you're given a second derivative and have to track your way all the way back up to the first. There's all sorts of variations, but these are the core ideas of section 3.9.